we're ready for the next presentation, which is by Yuliia Prykhodko. I'm sorry for the bad pronunciation of your name, and you're from the university called Yuri Kondrachuk Poltava Polytechnic in Ukraine.
Good afternoon. Our best wishes from Poltava, Ukraine. The topic of my work is the change of stress-strain state in biaxial banded reinforced concrete T-section beams depending on the load. The authors of this work are Yuliia Prykhodko, it's me, and Andrei Pavlikov, my supervisor of PhD thesis. We are from National University Yuri Kondratyuk Poltava Polytechnic. In today's world, the building industry is still considered to be one of the most important and influential in the world. It is connected with all economical and political spheres of social life. For the development of building industry, it's necessary to constantly improve and automate methods of calculation of building structures. In this case, an important step is the use of stress-strain state modeling method in order to analyze the possibilities of the elements work under compression, biaxial bending, and torsion. Particular attention is attracted by the necessity for process-changing knowledge of the stress-strain state parameters in the normal section of the reinforced concrete T-section beams. Especially important is the knowledge about the compressed zone shapes, which are determined by the position of neutral line in the cross-section through the parameters. They are theta is an angle of neutral line inclination, x is the height of the concrete compressed zone, and eta sub m is the value of concrete relative strength level in the most compressed fiber. In our work, we have identified possible shapes of the compressed zone for biaxial banded T-section beams. They are triangular, trapezoidal case 1, trapezoidal case 2, pentagonal case 1, pentagonal case 2, and hexagonal. For each form, in the process of integration, analytical dependencies are obtained, by which it's possible to determine the coordinates of stress resultant application in such zones. For better visual perception of stress-strain state models, in the normal section of the reinforced concrete T-section beam were constructed. To create the stress-strain state model of the banded reinforced concrete T-section element, a nonlinear diagram of the stress-strain relationship for the compression concrete was used. For the convenience of theoretical research of the stress-strain state, the stress distribution law in the coordinate system x sub 0, O sub 0, Y sub 0, depending on the coordinates x sub 0 and y sub 0, with k is equal to 2 was used. This made it possible to determine the stress value at any point of the reinforced concrete beam cross-section. The stress distribution law in the compressed concrete zone of the normal cross-section has the form shown on this slide. There, F sub CD is the calculated value of the concrete compressive strength. X here is the height of the concrete compressed zone. Eta sub M here is the value of the concrete relative compression strength level in the most compressed fiber. x sub 0 and y sub 0 are the coordinates of the point that is considered. And also theta is the angle of inclination of the neutral line to the horizontal axis. For your attention, there are given the formulas of stress resultant in the concrete compressed zone N sub C and its application coordinates x sub 0 and C and y sub 0 and C for different forms of compressed zone. Here you can see triangular shape. The stress resultant N sub C is equal to this expression. During integration, we can find that N sub C is equal to this formula, where omega sub 1 is the completeness coefficient of the stress distribution diagram in the compressed concrete zone of triangular shape under biaxial bending. Application coordinates x sub 0 and C and y sub 0 and C of stress resultant NC in the compressed concrete zone is equal to these expressions. In these formulas, S sub C x0 and S sub C y0 is equal to these expressions, where phi sub x1 and phi sub y1 are the completeness coefficients of the stress distribution diagram in the compressed concrete zone of triangular shape under biaxial bending. Here you can see trapezoidal shape case 1. The stress resultant N sub C in the compressed zone of concrete for this case is equal to expression this. Components C sub S sub C x 0 and S sub C y0 for finding the coordinates x sub 0 and C and y sub 0 and C of stress resultant NC are equal to the expression this and this, where phi sub x2 and phi sub y2, the completeness coefficients of the stress distribution diagram in the compressed concrete zone of trapezoidal shape, case 1, under biaxial bending. Here you can see trapezoidal shape, case 2. The stress resultant NC and sub C in the compressed zone of concrete for this case is equal to this expression. Components S sub C x0 and S sub C y0 is equal to these expressions. Here you can see pentagonal shape case 1. The stress resultant N sub C in the compressed zone of concrete for this case is equal to this expression. Components S sub C x0 and S sub C y0 are equal to these expressions, where phi sub x4 and phi sub y4, the completeness coefficients of the stress distribution diagram in the compressed concrete zone of pentagonal shape, case 1, under biaxial bending. Here you can see pentagonal shape case 2. The stress resultant N sub C in the compressed zone of concrete for this case is equal to this expression. Components S sub C x0 and S sub C y0 are equal to these expressions. Also phi sub x5 and phi sub y5 that are the completeness coefficients of the stress distribution diagram in the compressed concrete zone of pentagonal shape case 2 under biaxial bending. Here you can see hexagonal shape. The stress resultant and sub C in the compressed zone of concrete for hexagonal shape is equal to this expression. Components S sub C x0 and S sub C y0 for finding the coordinates x sub 0 and C and y sub 0 and C of stress resultant and sub C are equal to these expressions. There are shown formulas for calculating the completeness coefficient of the stress distribution diagram. This table shows the formulas for the triangular and trapezoidal forms of the compressed zone. Formulas for pentagonal and hexagonal forms are similarly derived. Using the equilibrium equation of stresses in the normal section of biaxial banded reinforced concrete T-section beam with the use of Microsoft Excel and AutoCAD software, models of stress-strain state at values eta sub m is equal 0.5 in case of trapezoidal form of compressed concrete zone, and eta sub m is equal to 1 in case of triangular form of compressed concrete zone are made. Using the presented models, analytical dependencies were obtained to determine the basic parameters of the neutral line position in the cross-section of the biaxial banded reinforced concrete T-section element. As shown by theoretical research, at low load levels, the stress distribution law has linear direction. With the increase of the load, the stress distribution diagram becomes warped. The height x of the concrete here of compressed zone and the angle theta of the neutral line inclination decrease. There are only two stress-strain state models of the biaxial banded reinforced concrete T-section beams, and the load change are presented. The algorithm for constructing models for other cases is similar. Consequently, it's possible to visualize the stress-strain state and to obtain the values of all its parameters, depending on the shape, which becomes compressed zone of concrete at any load level. Representing the process of stress-strain state changing by modeling with the use of a nonlinear diagram for the stress-strain relations description in concrete allows to determine with great accuracy all its parameters. The obtained formulas for their calculation allow to determine with sufficient accuracy the bearing capacity of biaxial banded reinforced concrete elements. Thank you for attention. Please ask your questions.
So thank you very much, Yuliia. So my pronunciation of your name was really very bad. I really apologize for
Not
this.
a problem.
Yeah. Are there questions from the audience? So if it is not the case, I will start asking questions. First of all, what is the aim of your research? To improve the efficiency of, because there are already now softwares for this kind of calculations. It's already possible to analyze this kind of cross sections with biaxial bending. What is the aim? To improve the efficiency of these softwares, or to allow for enhanced calculation?
We have maybe two aims, to not only to automate, but also to have a possibility to find stress, to to know stress strain model of T-section beam using different levels of load, and to know the stress level in every point of cross-section, and also to automate this program to make our life easier, because not everyone wants to calculate everything by hand, and it's easier for other students and other people, maybe engineers even, to use programs where they can input some data, but not to calculate it by hand.
Yes. Okay. So, are there other questions?
Can I add just something?
Sure.
Thank you, Yuliia, for your presentation. It's Marta Resultant speaking. As Professor Muttoni was saying, actually, there are several projects and also several software that actually already do this using the fiber models approach. So basically, now, if you look at a commercial software, open source software, but also other software, for example, I working on that, and my university developed the software on that. So the problem of cross-section of different shapes under biaxial bending in terms of resistance is quite already studied, and there are a lot of software that are able to predict with a good accuracy the moment capacity of different kind of cross-section and the bending moment. So the great issue today is about the deformation capacity. So what we are working now, when we look at the axially bended elements, so not only beams, but also columns, is about ductility. So are you probably planning to extend your research looking at the deformation capacity of your elements and not only at the bending moment capacity?
Using other programs, or
yes,
or using deformation, not these formulas, but deformation model. Yes, you mean, because the sound is not good.
Oh, sorry. I repeat. So basically, what I was saying is that the problem of predicting the bending moment capacity of cross-section under biaxial bending is quite already established, and there are a lot of software and analytical methods that predict with a good accuracy the bending moment capacity of such cross-section. So my question is, how are you going to proceed with your research project? Are you going to look at other aspects like the deformability, so the ductility of these kind of members? So what are you going to do next?
Yes, it's only a theoretical part, and maybe till the end of the year we want to do experimental work, and we will compare our theoretical maybe investigations or data in theoretical with our experimental data with different. Yes, we will get deformation from experiment, and then we using this deformation we can compare the stress level in experimental and in theoretical work, and then we will give maybe some recommendations how we can use our theoretical data, and what is the difference between this data.
I
So
suggest
we will test it.
Yeah.
Thank you, Yuliia.
Thank you, Yuliia. There is a question from the audience by Andrei Setyavan. Thank you very much. He is thanking you very much for your presentation. What is the main benefit or main feature of your proposed stress-strain approach compared to the usual interaction diagram used in practice?
In practice, there are a lot of a lot of elements with T-shape form, and we can use our investigation not only for beams, also not only for beams, but beam elements. They are calculated in different parts of buildings, so I can see big.
Yes, but for instance, in my, what we use in our design office, for instance, and there, for sure there are, and many, I can imagine that many people can work in this manner. We have a software which allows calculating any cross section. It can be a T-beam, it can be a flanged beam, or on the bottom, it can be even the cross section of a bridge with a very complicated cross section, just assuming the stress strain relationship of the Eurocodes, for instance. So I had a similar question as Andrei. What is the benefit assuming this kind of analytical solutions? Because it works only for T-shaped cross sections, right?
Yeah, yes, my investigation is for T section, but there are also existed for rectangular forms, yes. And what about practice? There are a lot of software programs, but there are also a difference between data of these software programs. So we can choose the most accurate program, and sometimes we don't know what to choose, one program or another, and
yes.
that's why we try to check.
Yeah.
May
I ask you? Sorry.
No. Ask, please.
Yeah. May I ask a question related to slide number 14, please? Previous one.
Yes.
Yeah. So you have the compression zone here, and yes. I don't understand. You also account for a tensile zone here.
Tensile zone of compressed zone here is here.
Yes.
And compressed ones.
Yes.
Here.
And what do you account for here with these tensile stresses here?
Please, one
yeah.
question.
So this is the compression zone.
This yes.
And but it seems that you have also a tensile zone here, right? Do I understand correctly?
Yes, tensile zone. Yes.
And where it comes from? You're accounting for concrete intention, or?
Yes, we have neutral line and the line of x, y, and have
yes.
Have the law of the law for compressed concrete zone. We can use in this law for tension zone, but in tension zone we use not sigma sub C, but sigma sub CT for tension zone.
Okay.
But analogical in other side, yes.
I see. So this is for a verification at ULS.
Yeah, tension stresses in tension zone are less. Yes.
And this is for a verification at ultimate limit state, right?
Yes.
Yeah. Okay. So, and this is allowed according to your standard?
Yes, we use not only standards of our country, but also Eurocode too.
Okay. Good. I have another general comment. Because it seems that you have chosen a stress-strain relationship which can be easily integrated, right? Is this the criterion to choose the stress-strain?
Integrals, yeah, we use integrals and the law of stress-strain, yes.
Yes, but with and of course you assume the assumption of you assume that plane sections remain plane. With respect to the so-called stress-strain relationship, here I have a comment. There are two methods in order to derive this such a stress-strain relationship. Yes. The one is, for instance, to test cylinders and to measure directly the stress-strain relationship. But here in this kind of problem, in fact, we have a quite different phenomenon. We are not discussing about the stress-strain relationship, but we are discussing about the distribution of stresses in the compression zone. And in the past, the most precise approach is to derive the so-called stress-strain relationship not directly from tests on pure compression, but by back calculation of bending tests. And this is the approach that has been done in the 50s and 60s, and this is the approach which is followed in many standards. For instance, the parabola rectangle stress distribution that we have in Eurocode, this is not derived from a compression test, but it is derived from the back calculation of bending test. And this describes much better the reality than the approximation based on compression test. And here, to me, I had my last question was, how do you derive exactly this stress-strain relationship that you're showing here?
Using integration.
But you will integrate it, but you have to assume a stress-strain relationship.
We use stress-strain relationship.
It's just a parabolic relationship.
Parabolic. We use for this moment we use these formulas and then.
But this formula, where it comes from?
It's not the straight formulas from Eurocode, but it's on the base of this formula, using parallel. Well,
I see.
One moment. Maybe parallel movements, because the axis. Maybe I will show.
Yeah. Okay. So I guess we are running out of time. We think
from this axis, from this axis, we move to y sub 0 by turning and moving parallel of this axis, and then we get that formula.
Okay, good. Thank you very much, Yuliia.
Thank you for.
Thank you very much. Thank you.